Why are the world's top seismic engineers suddenly obsessed with pre-colonial Filipino architecture? From Tokyo to San Francisco, structural engineers are abandoning billion-dollar technologies to study humble village houses made of bamboo and palm leaves. They've discovered that the traditional Bahay Kubo contains a secret organic dampening system that modern physics is only beginning to understand. We're diving deep into the flexible geometry of these structural masterpieces to reveal how ancient tribal designs can withstand tectonic forces that would level contemporary skyscrapers. This isn't about nostalgia, it's about survival in an increasingly unstable world. February 2025. A magnitude 7.8 earthquake strikes the coast of northern Philippines. In nearby cities, modern concrete towers, built to the latest international codes, reinforced with steel, engineered with cutting-edge computer simulations, sustain catastrophic damage. Structural cracks, collapsed floors, buildings deemed uninhabitable. But in rural communities dotted across the affected region, something remarkable happened. Traditional Bahay Kubo houses, simple bamboo structures with thatched roofs, some over 50 years old, remained standing. Not just standing, but virtually undamaged. Residents walked back into their homes within hours. Engineers arrived expecting to document primitive luck. Instead, they discovered sophisticated engineering that had been hiding in plain sight for centuries. What these ancestral builders understood intuitively, modern science is only now beginning to quantify. The crisis of rigidity in modern construction had met its unexpected solution in the flexibility of indigenous wisdom. The revelation triggered a fundamental rethinking in global engineering circles. For over a century, modern architecture operated on a simple principle: make buildings stronger, heavier, more rigid. Pour more concrete. Add more steel. Create structures so massive that seismic forces couldn't move them. But this brute force approach has reached its limits. Recent disasters in Turkey, Japan, and California demonstrated that rigid structures, no matter how reinforced, eventually meet forces they cannot resist, and when they fail catastrophically. Elite architectural firms worldwide are now pivoting toward biomimicry, learning from nature's flexible, adaptive designs. And at the center of this revolution is the Filipino Bahay Kubo, a structure that generations of Western engineers dismissed as primitive. Today, firms like Arup, Baffled, and Kengo Kuma and Associates are studying these houses not as cultural artifacts but as high-performance seismic isolation systems that challenge fundamental assumptions about structural engineering. Look closely at a traditional Bahay Kubo and you'll notice its distinctive shape: a steeply pitched hip roof, elevated floor, open walls. This isn't aesthetic choice, it's aerodynamic precision. The hip roof design creates a profile that naturally sheds kinetic energy from both earthquakes and typhoons. When seismic waves strike, the structure's shape channels forces around and through it rather than absorbing them directly. The steep pitch means typhoon winds flow over and around rather than pushing against large surface areas. Structural engineers analyzing this geometry discovered something fascinating. The traditional proportions, roof pitch angles, height-to-width ratios, floor elevation, represent optimized solutions arrived at through centuries of trial, observation, and refinement. No computer modeling. No simulation software. Just generations of builders observing what survived storms and earthquakes, and what didn't. The result? An organic optimization process that produced remarkably efficient structural forms. But the shape is only part of the genius. The real innovation lies in how Bahay Kubo structures are assembled. Traditional construction uses no nails, no screws, no rigid fasteners. Instead, builders employ lashing, binding bamboo poles together with flexible rattan or abaca fiber. To modern engineers trained on bolts and welds, this seemed dangerously weak. The reality is precisely the opposite. When seismic forces strike a rigidly fastened structure, stress concentrates at connection points. Bolts shear. Welds crack. Rigid connections become failure points. But lashed joints? They flex. They give. They dissipate kinetic energy through micro-movements that rigid connections cannot accommodate. Japanese researchers testing traditional Filipino lashing techniques discovered they outperform modern steel fasteners in seismic scenarios by allowing controlled movement that prevents catastrophic failure. The weakness was actually sophisticated engineering, designing for flexibility rather than rigidity, for energy dissipation rather than resistance. The material itself holds secrets. Bamboo seems fragile, hollow, lightweight, bendable. Yet it possesses a tensile strength comparable to steel while weighing a fraction as much. The secret lies in bamboo's internal structure. Longitudinal fibers running the length of each culm, reinforced by dense silica deposits at nodes. This creates a natural composite material, organic fibers in a silica matrix, that's remarkably similar in concept to modern carbon fiber composites. Engineers at MIT and Stanford have analyzed bamboo's cellular architecture and found optimization that human-designed materials are only beginning to achieve. The hollow cylinder shape provides maximum strength-to-weight ratio. The node structure creates regular reinforcement points. The fiber orientation provides strength in tension, compression, and flexion simultaneously. Nature spent millions of years perfecting this material. Filipino builders spent centuries learning to harness its properties. Modern engineers are now reverse engineering both achievements. At the molecular level, bamboo contains something even more remarkable: high silica content that creates natural dampening properties. When stress waves pass through bamboo structures, the silica fiber matrix absorbs and dissipates energy. Engineers call this the living hinge principle. The material bends without breaking, then returns to its original shape. Unlike concrete, which develops microfractures under stress that accumulate over time, bamboo can undergo thousands of stress cycles without permanent damage. University of Philippines researchers demonstrated this by subjecting traditional Bahay Kubo structures to simulated earthquakes equivalent to magnitude 8.0. The structures swayed dramatically, movements that would shatter rigid buildings, then returned to rest position completely undamaged. The entire structure acts as a three-dimensional shock absorber, working in harmony with seismic forces rather than fighting against them. This represents a fundamental philosophical shift. Don't resist nature's power, flow with it. Beyond seismic performance, bamboo offers solutions to another modern crisis: carbon emissions. Concrete production accounts for approximately 8% of global CO2 emissions. Steel production adds another 7%. Together, these materials, the backbone of modern construction, represent a massive environmental burden. Bamboo, by contrast, is carbon negative. It absorbs CO2 as it grows, reaching structural maturity in 3 to 5 years, versus decades for timber, and requires minimal processing. Under 2026 global carbon tax standards, the economic case for bamboo becomes compelling. A traditional Bahay Kubo's entire material footprint, bamboo, rattan, palm thatch, can be grown, harvested, and processed with less than 5% the carbon emissions of an equivalent concrete structure. Multiply this across millions of buildings and the climate impact becomes staggering. Filipino ancestral builders created sustainable architecture not through ideology but through necessity, using locally available, renewable materials. Modern architects are rediscovering that environmental sustainability and structural performance aren't competing priorities. They're complementary when you design with nature rather than against it. Perhaps the most ingenious aspect of traditional Bahay Kubo design is barely visible: the foundation system, or more accurately, the deliberate absence of one. Traditional structures don't use concrete footings anchored deep into earth. Instead, they employ a floating system, bamboo posts resting on flat stones or hardwood pads. To engineers trained on deep foundations and rigid anchoring, this seems structurally unsound. But it's actually brilliant seismic isolation. When earthquake waves travel through ground, rigid foundations transmit those vibrations directly into the structure above. The Bahay Kubo's floating foundation decouples the house from the ground's movement. The posts can shift slightly on their stone bases, absorbing and redirecting energy before it reaches the living space. Modern buildings achieve similar effects using expensive base isolation bearings, sophisticated mechanical systems costing thousands per unit. Filipino builders achieved equivalent performance using shaped stones and careful positioning. Ancient base isolation, perfected through observation and incremental refinement across generations. The question facing modern engineers: can these principles scale beyond single-story village houses? The answer is emerging in projects worldwide. In Singapore, architectural firm Woha is designing multi-story residential towers using bamboo as primary structural material, employing traditional lashing techniques adapted with modern engineering analysis. In Tokyo, researchers at the University of Tokyo are developing smart bamboo systems. Bamboo culms reinforced with bioresins and connected using 3D printed joints inspired by Filipino weaving patterns. These aren't novelties or experiments. they're serious structural proposals for high-rise construction in seismically active zones. The International Building Code is being updated to include bamboo as an approved structural material, a recognition that would have seemed impossible a decade ago. What's enabling this transition? Computer modeling that can now quantify and verify what ancestral builders knew intuitively. Flexibility, when properly designed, outperforms rigidity in dynamic load scenarios. Beyond seismic performance, bamboo construction offers another critical advantage: rapid disaster recovery. When earthquakes damage concrete and steel buildings, reconstruction requires heavy machinery, specialized materials, extended timelines. Damaged bamboo structures? Communities can often repair them locally using available materials and traditional skills. This decentralization of construction capacity is increasingly valuable in climate-vulnerable regions facing more frequent disasters. After Typhoon Haiyan devastated the Philippines in 2013, communities using traditional bamboo construction techniques rebuilt functional shelter within weeks. Nearby areas dependent on conventional construction methods remained displaced for months or years, waiting for materials, contractors, and funding. The ability to rebuild quickly using local resources and knowledge represents resilience that money cannot easily buy. As climate instability increases disaster frequency, this self-sufficiency becomes not just culturally valuable but economically and socially critical. Traditional building methods, dismissed as backward, now appear remarkably forward-thinking. The cutting edge of this architectural revolution is happening right now. In 2026, several pilot projects are demonstrating how ancient wisdom integrates with modern technology. In Cebu, Philippines, a 5-story mixed-use building employs engineered bamboo, culms that have been treated with boron solution for durability, then assembled using computer-modeled joinery inspired by traditional Filipino basket weaving patterns. The connections are 3D, printed from bio-based resins, creating precise fits while maintaining the flexibility that makes bamboo seismic resistant. In California, a research team is developing smart bamboo sensors that can detect structural stress in real time, essentially creating buildings that monitor their own health. These innovations aren't replacing traditional knowledge, they're enhancing it, applying modern precision to time-tested principles. The result: structures that combine ancestral resilience with contemporary performance monitoring. This synthesis represents architecture's future, not tradition versus innovation, but tradition informed by innovation, innovation grounded in ancestral wisdom. We stand at a crossroads in architectural history. Climate change is increasing seismic activity, intensifying storms, and demanding dramatic reductions in construction-related carbon emissions. Conventional building methods, concrete, steel, rigid design, are simultaneously too expensive, too polluting, and too vulnerable for our changing world. The solution isn't entirely new technology. It's recognition that pre-colonial Filipino builders, working with observation and iteration across generations, solved problems we're only now understanding. The Bahay Kubo isn't primitive, it's sophisticated biomimetic engineering. The next era of global architecture requires this humility, acknowledging that indigenous ingenuity, developed through intimate relationship with specific environments, often outperform solutions designed in isolation from natural systems. When Tokyo's next major earthquake strikes, or California's inevitable Big One arrives, the buildings most likely to survive won't be the tallest, heaviest, or most expensive. They'll be the ones designed with principles first perfected in Filipino villages centuries ago: flexible, adaptive, working with nature rather than against it. That's not nostalgia. That's survival through ancestral intelligence. The world's most advanced seismic engineers are studying bamboo houses in Filipino villages. Not because they're quaint. Not because they're traditional. Because they work better than billion-dollar modern alternatives, and they've been working for centuries. Sometimes the most advanced technology is the oldest. Sometimes survival requires looking backward to move forward. The Bahay Kubo isn't the past. It's the blueprint for the future.